Welcome everyone following along on YouTube and maybe anyone joining on Discord later. Um, Welcome to this apart talk where we are listening to Alex talk about the Neuron to Graph paper that arose from a hackathon all the way back in November on interpretability, an alignment jam, of course. And we worked with him to publish it as well. So it's joint work with Neil Nanda, a bit of me, Yonis Kanstas, Shea Cohen, and Faisal Baris. And it's been published at ICLR RTML workshop, and I believe even going further than that. So I'll just give the stage straight to you, Alex, and let you take it from here.
Perfect. Thanks for the introduction. Yeah, so it's currently in submission to Europe, so fingers crossed, but no decision yet. But yeah, so yeah, I'm excited to talk about this work. So it's called Neuron to Graph. The idea is that it's a new tool for interpreting neurons within language models, so a new tool for mechanistic interpretability work. So to give you a bit of background on the problem, one aspect of mechanistic interpretability work that we might be interested in is trying to understand what do individual neurons in the MLP layers within language models actually respond to? What is their behavior? With the idea that if we want to understand the whole model, one way to get traction on this is to sort of understand the individual components and then how they sort of compose together into larger circuits and perform larger functionalities. And a natural sort of unit of investigation is the individual neuron level. So there are reasons to think maybe there are other sort of avenues that might be useful as well, but neurons are quite a natural place to start. But there's been some challenges in interpreting them, particularly there's not necessarily good tools to do it. So if you compare to, say, vision models, where you can perform feature visualization and directly sort of optimize an image to understand what this particular neuron responds very strongly to, which gives sort of more causal evidence in a way of a neuron's behavior. We don't really have that same capability in language models. So what I was interested in was sort of taking some steps towards a better tool for understanding these neurons. And the current way that we tend to do this is by looking at the dataset examples that are most activating to a particular neuron. So if we've got a particular language model like this one, then one thing we might, or the current way we often do this, is that we process a bunch of data, like the whole trained data set with the model, and we record all the activations of a particular neuron that we're interested in, and collect the examples that are most strongly activating to the neuron. And the idea is that these examples sort of capture the neuron's behavior sort of concisely. But these have various sort of limitations. So there tends to be quite a bit of redundancy. So often the most activating examples will all be quite similar and may not fully express all of the context in which a neuron activates. They also don't provide sort of direct evidence of what is important. You have to just sort of look for patterns across the examples. So like for this set of examples, we see that, it's the neurons responding on the token accept that we've highlighted in particular context. And it seems like there's, something about there needing to be a token about all or everyone or sort of, everything seems to be important. And then there's some other text that maybe isn't important, but we're always sort of relying on just trying to generate a hypothesis just on the patterns that we observe in text, but not directly measuring like, oh, what parts of this are necessary for activation. And it's a very manual process. So researchers might, look at dataset samples for each individual neuron, which doesn't necessarily scale to large language models. So we might want to take steps towards more automated tools. And one key thing there is that we might want to be able to automatically measure how well our sort of hypothesis actually captures a neuron's behavior. At the moment, we might have, this sort of idea in our head about what this neuron is doing, but we don't necessarily have direct evaluations of how well does that actually capture the neuron's behavior. So these were the sort of things that I wanted to try and make some progress on. So the initial idea that I sort of pursued in the hackathon and a bit beyond was to just iterate on improving the dataset examples themselves. So one thing when you start looking at these dataset examples that you see is that they often have a lot of extraneous context that you don't really need for activation. So they'll often be quite long, 1,000 tokens or so, whereas only maybe 10 or 20 tokens are actually the key part that is necessary for activation. So the first step that I wanted to do was take this, big dataset example and just extract out the most important bit, the most informative bit for activation. So the way I basically do this is by pruning. So given a big dataset example, we basically find the token on which the neuron activates most strongly. And that's sort of the key token for that example. And then we basically strip out all the sort of rubbish after that because it's a causal language model. So anything after that can't affect activation on that token. So we sort of get rid of all of that, leaving like a little bit of context of like the last bit of the sentence. And then we basically then iterate backwards through the prompt, gradually adding a token at a time, and then measuring the activation of the neuron on the sort of truncated prompt to see how it sort of recovers as we add new tokens. So if we have up here a prompt like the thought didn't even cross my mind, where cross is the key token, then we start by just giving the model the token cross and see how strongly does this neuron activate on cross, and maybe it doesn't activate very strongly at all. So then we add even and we go, okay, how strongly does the model activate on even cross? And maybe it's a little bit stronger, but still quite weak. And we keep doing this, gradually adding neurons until we've recovered activation on the main token or the key token sufficiently to consider that to be like a useful prompt. So we generally say if it's like above 50% of the activation on the full prompt, then that's the sort of extract that we need. So once we've got this sort of minimal extract, we can now perform other operations on this without having to worry about all the extra stuff. So the next step is we want to measure how important is each context token for activation on the key token. So again, if we look at this prompt up here, we've got the key token here, and in this top row, we've got the activation of the neuron on each token in the input. So we can see that this is actually the normalized activation, by the way. So this is just normalized between 1 and 0, with 1 being like the strongest activation observed on any token for that neuron. So we can see the neuron activates very strongly on cross and basically not at all on any of the other tokens. So then what we want to establish is for these context tokens before the key token cross, how important is each of those for activation on this key token? And the way we basically do this is by masking each token with a special like padding token, and then measuring how much does that change the activation of the neuron on the key token. So for example, if we mask the token thought, then we find that activation on the key token drops massively. So specifically, it would drop to about 0.1. And so the importance is just directly related to that. It's just 1 minus whatever the new normalized activation is. So the idea is that the more the activation decreases, the more important the mask token was for neuron activation. And this gives us this sort of heat map of importance of each token for activation on the main token. And this gives us some sort of direct evidence of what context is necessary for activation, and allows us to focus our efforts on further investigations on these important tokens. So once we've got this information, we then want to try and explore a bit better the space of inputs that are activating to this neuron. So as I said, there's often a lot of redundancy in these max activating data examples. And so what we want to try and do is create sort of counterfactuals of like, okay, well, if I change this token, what happens to the activation? Does it still activate strongly? Does it stop activating completely? And this can sort of sketch out a better picture of overall neuron behavior. So the way we do this is we basically take all the important tokens, so basically any tokens that have an importance above a certain threshold. I think for this example that the threshold was something like 0.8. And we mask those tokens, and then we give the masked input to a model like BERT and get it to predict what other tokens are likely to appear in the place of that masked token. So given this context of like, if we're trying to find other things for thought, we would have like, given the context of like the mask didn't even cross my mind, what other tokens are likely to appear here? And so BERT will produce a load of predictions, and then we can take those new examples and measure, okay, how does the model respond to those instead? And this allows us to sort of automatically explore the space of model activation or neuron activation more completely. And what we can see is that when we do stuff like this, it gives us a better idea of of what the neuron is responding to. So, for example, for this, when we're replacing thought, we can see that if we have the idea didn't even cross my mind, that activates the model pretty strongly, still like sort of 70% of the original activation. Whereas the words didn't even cross my mind, the activation drops a little bit to only about 50%. So this might give us some idea that, you know, maybe idea is sort of more semantically similar to thought. And so maybe that's why we have this stronger activation. And if we have, you know, 10 or 20 of these different things, we might be able to pick up these patterns more easily and get a clearer sense of the boundaries of neuron activation and what exactly it doesn't respond to. Because I think for this neuron in particular, basically all the top examples were just the thought didn't even cross my mind in different contexts. So there was none of this additional context that you can see to delineate behavior. Similarly, we can replace the key token and see what other key tokens it might respond to. And in this case, we find that it does respond relatively strongly to other key tokens that are semantically similar. So like the thought didn't even escape my mind or didn't even enter my mind. Interestingly, activation drops off quite a lot when we go to the thought didn't even touch my mind. And when you look at more examples, augmented examples, you tend to see this pattern for this particular neuron where it responds more strongly to words sort of about movement, like cross or escape or enter, compared to other words that could fit in that context. And so this demonstrates how this this method can sort of, more clearly delineate neuron behavior. But there are still some limitations with this method. So we're still operating only at the level of sort of examples, although we've expanded our examples and we have some additional enrichment via the importance information. So we're not purely pattern spotting. We're still only looking at these examples, and we also notice that there's quite a lot of still some redundancy across examples, so that, you know, in some way we could represent this more concisely because there's a lot of common information between these. And we still have no way of measuring, well, how well does this sort of capture neuron behavior? Like if we form a hypothesis off these examples, well, are we seeing like everything, or are we only seeing a small sort of piece of neuron behavior? So that's what motivated the next stage of development, which was to create neurontograph. So the basic idea is that the initial process is the same. So we start with these dataset examples for a particular neuron. We compute all the activations, and so we have the tokens of which this particular neuron strongly activates highlighted in red. Then we do our pruning step to extract just the most important bits, and the importance measuring step where we say, okay, how important is each of these tokens for activation on the key token? And so this is the sort of output that we just saw in a slightly different format. we do our augmentation step where we say like, okay, all except one, everyone except you. And then we get BERT to come up with other replacements for these important tokens. And so for this particular example, we find that everything is also activating, which we're maybe missing just from the pure dataset examples. But then the key thing is that we then build this graph that more concisely represents what the neuron responds to, and also allows us to evaluate to what degree the sort of examples we've seen capture the overall neuron behavior. And I'll tell you a bit more about that in a minute. But it sort of provides this concise representation of, with greater variety of inputs, these measurements of importance and this overall measurement of quality. So the way this graph building works, so we start with our sort of enriched examples up here. So this is like what we saw previously, where we've got our activating tokens highlighted in red, then we've got our important tokens highlighted in shades of blue according to their importance, and then we've got some unimportant tokens that we're saying in this case sort of didn't meet the threshold of being worthy of consideration. They don't seem key for this particular neuron, and so we have this idea that maybe we need some token there, but we don't need any specific token, so we allow those to sort of vary and don't include them in our graph. So what we want to do is take these sort of enriched examples with this importance information and convert them to a different representation that captures the behavior more concisely in a clear way, but also allows us to sort of evaluate the quality of this representation. And so what we do as a first step is we create what's called a trie, which is basically just a way of representing text in a sort of tree-like format. So what we basically do is we start at the activating token for a particular example, so in this case cross, and we start at the root token of the trie, and we say, does the root token have cross as a child node? And in the first case it doesn't, so we add cross as a child. Then we work backwards, skipping over the unimportant words. Just seen I've put the ignore token slightly the wrong place, but we then would say cross. We then have an unimportant token, so then we add a special sort of ignore token saying like we need something here, but it doesn't need to be the specific token that we saw in the example. And then we keep iterating backwards and adding the important tokens where necessary, or the unimportant tokens. And this builds up this sort of tree structure that represents any path through this sort of trie represents one of the enriched examples that we looked at. And what this trie allows us to do is to actually process text and output predicted activation. So on the leaf node of each trie, we actually store the activation of the neuron on this path. So for example, if on the input the thought didn't even cross, the neuron activated with a normalized activation of say 0.9 on cross, then we store that information on the leaf node for that path through the trie. So it keeps flicking over. So what this allows us to do is when we have new input text, we can go through each each token of the input text and ask, does the preceding context match any path through this trie? And if it matches a path through the trie, then we can output the final activation on a leaf node as our prediction of the activation on that bit of input text. And importantly, because of our enrichment of examples through the augmentation, and because of the fact that we ignore some tokens using the importance mechanism, we can sort of generalize beyond the original set of input dataset examples to have a representation that captures a more broad set of behaviors than was just captured in that original example. And this provides us a way of automatically measuring, okay, how well does this try actually capture the neuron's behavior? Because we can say, we can give it some input text, and for each token in that text, we can measure our predicted activation using the try by processing it with the try and outputting. If it reaches a path through the try, then we output the predicted activation or the observed activation. And then we can compare those predicted activations to the activations of the real neuron. And so it gives us this way of directly comparing the try representation to the real neuron. So we can evaluate at scale how well these tries, we can build them fully automatically and evaluate them by comparing them to the ground truth sort of neuron activations to get an automatic measure of the representation quality. But this try representation is sort of somewhat difficult or somewhat verbose. It could be more concise because there's some repetition, particularly for the larger tries, which can get a lot bigger than this. There might be a lot of repeated information or areas where we might be able to gain more insight by representing it in different form. And so for that, we converted to this sort of graph form. And this is a simple transformation where we basically, if we consider each sort of layer of the try according to the sort of the node depth, we basically collapse all the identical tokens within a sort of layer of the try into a single node. We remove all the ignore tokens, which, because they contain sort of unimportant information, they're sort of only holding syntactic structure. So the current representation is we just ignore them, we get rid of them for their visualization purposes. And then we color nodes according to either their level of activation. So for the final end nodes, we color them according to their activation in red. So the brighter red they are, the more strongly they're activating the neuron. And we color the context tokens according to how important were they for activation. So the brighter blue they are, the more important they are. And so this gives us an immediate sort of visual indication of the most activated tokens, the most important tokens, and the structure of how they link up in this sort of concise representation. But it's backed by this try representation that we can automatically sort of measure the quality of. So looking at some results, what we've basically done here is for each layer in a 6-layer model, we build a graph using neuron to graph for every neuron in that model, and then off a sort of training set of dataset examples. And then we have a test set of dataset examples that are completely a disjoint set. And we measure how well does neuron to graph predict the token activations on the held out test set compared to the ground truth neuron. And what we basically find, we compare to a couple of baselines, which I won't go into detail on now, but they're basically sort of a recall focus baseline and a precision focus baseline. What we basically find is that neuron to graph does a pretty good job of capturing neuron behavior in the early layers with like relatively high recall with moderate precision. But this falls off as we go to later layers. So the recall falls off, and in particular, the precision gets worse. And this is probably because later layers tend to have more complex behaviors. So one common idea in machine learning is that the early layers in a model are capturing sort of simpler features. Like maybe layer 0 is just responding to individual tokens, sort of regardless of context. You might just have a neuron that just responds to the token the, or just word or something with no additional context. But then later neurons will respond to maybe higher level semantic concepts. So it's harder to capture that sort of broad range of all the things that the token might respond to. And at the bottom, we have sort of an illustration of a couple of neurons within this model, one from layer 0 and one from layer 3, which are sort of somewhat typical of the layers. So for the layer 0 one, we see we have this much simpler behavior where the neuron's activating on the token 2 when it's preceded by some token relating to beginning or starting something. Whereas in the later one, we have this sort of these longer dependencies with this more sort of semantic context relating to sort of software and software licensing. And it's much more likely that we've not sort of fully captured the context in which this neuron activates because of its more complex behavior. But overall, neuron to graph has sort of utility in its ability to capture particularly early neuron behavior and particularly particular types of behavior. So like for more syntactic style neurons, it might do a better job than more semantic style neurons. And even in the later layers, there will be quite a decent proportion of neurons where it does a very good job of capturing the neuron behavior. And there are others where it might struggle. So it provides utility sort of throughout the model. And then if we take a look at what does this new sort of representation enable and how does it allow us to explore the model in new ways? So not only can we sort of automatically build these representations and evaluate how well they're working, but we've now got this sort of, if we run neuron to graph on all the neurons in language model, we've now got these sort of artifacts that allow us to explore the neuron explore the model in new ways. So one thing that we can do a lot more easily now is search for particular neurons. So we might want to find neurons that activate in a particular context or activate on a particular concept or a particular token or set of tokens, or we might want to find ones that require a particular context to activate. So only when this particular token or this set of tokens is in the context. And having this sort of representation of the important context tokens and the activating tokens allows us to do this search in a way that dataset examples don't, because if we were just naively searching the dataset examples for the context neurons, we would have no idea if, you know, a particular token was actually important for activation or if it was just some random token that happened to be in that prompt. So this representation sort of facilitates that sort of new method of exploration. And as well as searching for like, say, you know, this particular context token and this particular activated token, we can also search for sort of patterns. So for example, we use this to discover this sort of neuron up here that seems to be sort of an in-context learning neuron. So what we mean by this is that it looks for a pattern that has appeared previously in text. And when the beginning of that pattern occurs again, it will increase the probability of predicting the later part of that pattern. So if we say we observe a pattern AB in our prompt, and then later on we see the token A again, then this increases the probability that we're going to predict some token B. And importantly for this particular neuron, it seems like from the graph and from the examples, it's a very general, like pattern-focused neuron rather than responding to particular concepts. It's very much responding to sort of any random pattern. I mean, these look like sort of nonsense because it's specifically responding to the pattern rather than the semantic information in the tokens. And we discovered this via the sort of search capability, looking for neurons that have a high incidence of tokens that are both in their context and in their activating tokens. So that allows us, the representations are facilitating a new way of sort of investigating the model and looking for particular behaviors automatically. So it suggested a bunch of these sort of in-context neurons fully automatically. We're also able to programmatically compare neurons. So for example, we can look for neurons which have a very similar representation automatically by comparing their sort of graph representations, comparing the neurons, the context tokens on which they activate and the activating, the context tokens necessary for activation and the tokens on which they activate. And if we can compare those for two different neurons, that gives us some measure of similarity, which we can use either to identify similar neurons or as a further development, we might be able to use it to identify sort of circuits of neurons. So early, for example, we might find that some early layer neurons are sort of composed into a later neuron that contains all of these sort of early behaviors. So it's sort of composing or like unioning over these simpler behaviors to have one more complex behavior that covers all of those cases. And you can imagine detecting this by looking for sort of neurons which are a subgraph of a later neuron. And this might allow you to automatically detect these sort of circuits of behavior. We have sort of an illustration of what this, how this could look down here. So this was sort of looking for neurons that are responding to import syntax in different languages. So these were discovered by searching for neurons that have import in sort of the context or in the activating tokens. And so for this sort of layer 4 neuron here, it responds to imports in Python of a bunch of different common libraries. And what you can imagine is that this neuron is composed of, say, a neuron that just responds to like import sys and import re and a neuron that responds to import time and a neuron that responds to import requests. And it sort of composes all those behaviors together into one. So what we might be able to do is look for these sort of composition neurons that automatically by looking for these sort of subgraphs in early layer neurons. So in this way, sort of neuron to graph provides this sort of new form of analysis. So to summarize and provide some further resources, neuron to graph is our new tool for investigating neuron behavior. So it will extract the most important part of a dataset example, identify or measure the importance of the context tokens, enrich those examples with further examples by exploring the local input space via using a model like BERT to identify other likely tokens, which better sort of sketches out the overall neuron behavior. And then it takes those sort of enriched and enhanced examples and creates this graph, try and graph representation, which both allow us to quantify how well does this graph capture neuron behavior fully automatically by comparing to the ground truth activations, as well as enabling new forms of investigation via searching these graph representations or comparing them automatically. So we both have this better quantitative measure of representation quality, as well as a new sort of qualitatively new way of investigating models from an interpretability standpoint. So if you're interested in finding out more, we have a couple of papers. I've put the most recent and longer version up here. A website that we're developing that will provide some more information and examples on of some of these neuron graphs. And we've also got a repo available with some of the code, which is at this stage still in a research sort of state, but we're developing into a package. And you can also feel free to reach out to myself or Fazil, one of my co-authors at these links. So yeah, thanks for listening, and feel free to ask any questions.
Wonderful, thank you. A little bit claps for me. All right, anyone in the audience who are interested in asking any questions are very welcome to raise their hand. And I see already now, invite to speak. You are invited to speak, so you can join the stage and ask any questions you have. Otherwise, while Botanium tries to figure that one out, one question I had is, we also saw earlier the automated interpretability work from OpenAI, and how does this relate to that? Does it outperform it or something like this? Because many people who have looked into the OpenAI tool as well have seen that, okay, sometimes it really doesn't actually represent what the neuron activation stands for. So I think one of their examples was the Marvel characters one. But there the activation was not on the Marvel characters. So yeah.
Yeah, so that's a great question. So I think they're very much complementary approaches. So they're basically tackling the exact same problem, and there's a lot of similarities that we came up with in terms of the, like, can we automatically evaluate it by having this sort of simulated neuron representation and this real neuron representation. So those things are quite similar, but the overall approach to building this representation is sort of completely different. Obviously, ours is sort of extracting this this kind of representation from the input texts, whereas the OpenAI one is trying to sort of generate some more natural language explanation of it from the text. So I think in that sense, they're quite complementary in that there are going to be strengths and weaknesses of each approach. So like, I think neuron to graph works particularly well for more syntactic neurons, where maybe it captures the structure very well. So particularly for like programming, I think it could be very interesting, like code models, because it can capture that sort of syntactic structure quite well, whereas it struggles a bit more with sort of semantic neurons, where a neuron might respond to a sort of a very wide range of concepts that is hard to like exhaustively represent and discover in this graph view, whereas that might be more concisely captured with sort of a natural language explanation by one of these models. So we don't have a direct comparison of like how well it works, because we were working on different models. And so, yeah, there's no direct comparison. But what I would suspect is that they each work well in different areas, but there are probably similar weaknesses. Like, I think they both probably perform quite a bit worse for later layers, for example, than earlier layers. So I think they're sort of complementary, have some different strengths and maybe similar sort of overall weaknesses.
Yeah, I think we both had so we have the graph from the table of later layer diminishing performance, right? And then
Yes, exactly.
OpenAI has the same
yeah,
one.
yes, exactly. It's like as you get into these later layers, like the sort of behaviors of these neurons are just a lot more complex and responding to sort of much broader context, or much sort of more difficult to understand feature. And that seems to happen across models and across techniques. So struggle with that.
Nice. Yeah. And I think Botanium's on the stage now, so you're very welcome to ask your question.
Thanks for the talk. I had a question about your results. I'm not sure to understand what each metric is in your table.
Sure. Let me go back to it. Okay, so if we take this first block here, so this is the results from neuron to graph. So these others are baselines that aren't too important. But basically what we have is we're measuring the precision, recall, and F1 of the predictions of the trie that we've built for that neuron compared to the ground truth activations of a neuron. So what we're basically doing is we're treating it as a classification problem. So we've got some input texts, and for each token in those texts, we gather the activation of the neuron on that token. So what we've effectively got is a series of like subsequences and the activation of the neuron on that subsequence. And then the task is to predict whether the neuron responded strongly on that subsequence or whether it responded weakly. So we stratify the neuron activation into either firing or not firing for simplicity. So rather than trying to predict the exact activation, you just have to predict, did the neuron fire, i.e. activate strongly on this token, or did it not fire, i.e. activate weakly on this token? So we basically set a threshold of neuron activation on a particular token and stratify it into firing or not firing. And then basically we say, can the graph accurately predict whether or not a neuron will fire or not fire on a particular context? So we have this sort of classification problem where for each subsequence in the text, we say, okay, the neuron actually fired. The graph says the neuron fired. So that's like a true positive. Or we have, the neuron didn't fire, but the graph says it is going to fire. So that's, a negative. And so we can use that to compute the precision, the recall and the F1 of the graph with respect to the ground truth neuron in the same way that we would for any other classification problem. And that gives us this automatic measure of correspondence between the predictions of the neuron and the actual ground truth activations. And that's what is shown here. And so we find that the recall is generally pretty good in that. So that's saying that the graph is quite good at saying when a neuron activated on a token, the graph is quite good at predicting that it did activate, but the precision isn't as good. So what that's saying is that it tends to over predict that the model will activate on more contexts than it actually does. So it's sort of not fully capturing all the context, and it's maybe overgeneralizing and saying that the neuron is going to activate on more context than it actually does. Yeah, does that make it clearer? Is there any other?
Yeah, and what about F1?
Yeah, so F1 is just a form of average between the precision and recall. So
Okay.
So it's just a sort of it's the harmonic mean. So it's sort of a way of taking into account an overall measure of the precision and recall of that system.
Okay, thank you.
No problem.
Nice. And another question I have is like, do you remember if this is comparable to the explanation score that OpenAI uses in their paper, and how does it compare?
So it's we could make it comparable. It's not directly comparable. So at the core, we're doing the same thing where we have some representation. So in our case, it's the graph representation. In the case of OpenAI, it's the like explanation plus simulation of activations based on that explanation. And then we're measuring the correspondence between those two. So how well does our representation correspond to the ground truth's activation? So in that sense, they're the same principle. We just take two slightly different approaches to measuring it. So whereas I turn it into a classification problem and I'm trying to measure, does the neuron fire or not fire, they look at it as more like a regression problem, and they're trying to say, what is the sort of correspondence between the predicted activation and the actual activation as sort of a correlation. So what's like the correlation of the two metrics? Whereas I say like, yeah, treating it as a classification problem, what's like the accuracy or the sort of precision of recall. So we could, if the OpenAI paper had come out earlier, we probably would have tried to do a direct comparison because it very much fits into the same framework, but we just happen to sort of use these two slightly different metrics for doing it.
Yep. Nice. And what do you see as some of the next steps? Of course, we talked about a little bit about it before as well, but yeah.
Yeah. So I think there are various steps. So I think there's sort of two obvious things. One is improving the representations themselves. So developing either better ways of capturing the neuron representation, better ways of representing the neuron representation. So concretely, one thing you might want to do is include some of the negative examples in the graph. So you might say, all these tokens activate it, but this one doesn't activate it. And that might give you a clearer picture of neuron behavior, because that's quite, I think, a common workflow for research is to try and sort of break the neuron. It's like, okay, well, it activates to all these things, but can I like push it outside of its range? Or maybe it's like, it doesn't activate to all these things. It only activates in this very specific thing. And so the actual negative examples that are close but don't activate are actually quite informative. And so maybe including them in the graph is quite useful. So that might be one way. Or maybe you could improve like the ability to augment and explore this space. So at the moment we're doing it at sort of a local level via substitution with BERT. But one of the things in the OpenAI paper they do is they generate like entirely new sentences using like GPT-4 based on the explanation. And this allows us them to like revise their explanations. You can imagine doing something more like that, where you're generating sort of wholly new examples rather than just sort of tweaking the ones you've got. So that's sort of on the side of improving the representation. There's sort of lots you can imagine there. And then the other side is, how can we use these representations to facilitate interpretability research in new ways? And so one of the things I sort of alluded to in the talk was maybe you can sort of discover circuits more automatically, because now you have this like representation that you can programmatically compare in certain ways. And so maybe this allows new sort of workflows or new sort of programmatic things. Or, you know, it might be that you have some behavior like the in context learning behavior, or some other stuff is like the I can't quite remember, but where you've got like oh, don't worry about it, but there are various interpretability results where you have this like mechanism of behavior often identified through like an attention circuit, and maybe you can look for neurons that are responding to it by like programmatically searching this representation for neurons that fit this particular pattern. So like the in context learning, where you've got this repeated pattern, or these other like algorithms, we might be able to find neurons that respond to these algorithms by searching automatically these representations. So I think those are sort of, yeah, the two avenues. Is like improving the representations, which could also be like unifying with the natural language explanation, stuff like this, or using the representations in sort of new ways.
Yep. Nice. And if there are more questions from the audience, just raise your hands. Another thing, just probably some of the last questions here, is that this looks quite like monosemantic and again syntactic, as you mentioned. Are there ways we can make them more responsive or more representative of polysemantic things? Like this seems as limitation dependent on this key token, or its derivatives, right?
Mm-hmm. Yeah, so in principle, there's no limitation neuron to graph to only discover sort of monosemantic things. So one of the interesting examples I didn't include here is that if you're capturing the various distinct and like disjoint behaviors in the dataset examples, they actually quite naturally separate into different graphs because there's not much overlap between them. So they kind of separate into these different behaviors that are like completely separate. You've got like these subgraphs that look completely separate. So that's another interesting thing, is that maybe it can enable some sort of separation of these polysemantic neurons, but that's sort of more speculative. So yeah, in principle, there's no limitation. I think in practice, it will generally work worse as it currently is for these more challenging neurons, say the polysemantic ones, or the generally semantic ones. So you can imagine another sort of improvement would be maybe you can generalize from looking for specific tokens to maybe looking for like an embedding representation of that token. So you get more of the semantic meaning. So you could enrich the graph with sort of more than the purely like text-based representation, to develop the semantic sort of capabilities better.
Yeah, so like instead of each node being a token, it would be a semantic subspace or something like that.
Yes, exactly. It's like maybe you find that the neuron responds to all these sort of similar tokens. So maybe you can identify like the embedding or like the direction in embedding space that like captures that set of tokens well and allows you to generalize beyond just the ones you've seen in like the dataset examples.
Yep, nice. And last question. Memory editing is of course quite hot, and we're very curious to be able to change the models as we reverse engineer what are some of the risky behaviors or biased behaviors or these sort of behaviors we don't want. So this can be used to search for neurons that are maybe, you know, playing a part in some sort of circuit for, you know, biases or something like this. Do you think we'll be able to just like Command F, Control F, find the ones that are about gender, remove them, and then we've solved we've solved the bias in models.
Yeah.
Yes,
it's
that was
definitely
a great answer.
cool, yeah. Exactly. Yeah. No, this is going to solve it. Yeah, this has cracked it. Yeah, it's probably not quite so simple. Although I do think that's a really interesting idea that we've also considered is like, can you identify, as you say, like say some neuron that responds that influences like the toxicity of the text, or some circuit that responds to like particular gender stereotypes or whatever. I think this could definitely be useful as a discovery tool for that sort of thing, as you say. The editing side is maybe more challenging. That there are various things like, say, removing those neurons, for example, or ablating them, can sometimes be misleading, because you might think, oh, I've got rid of this neuron that responds to gender stereotypes, and therefore it will solve the problem. But either the model sort of compensates, or now you've got some sort of hidden representation of this. Instead of it being in one clear place, the model sort of changes to represent it across neurons, and so you've actually just made the situation sort of murkier. But there is some interesting research doing this. So OpenAI quite a while ago found that in one of their, might have been pre-GPT, I think it was an LSTM model that they trained as a language model. They found that there was one neuron, and the activation of that neuron corresponded like very strongly to this the like sentiment of the text that was produced. So it was like very predictive of the sentiment of the text. And then what they found is that because that was localized to like a single neuron, they could artificially like set the activation of that neuron to a particular value, and that would correspondingly influence the sentiment of the output text. So like if you set the activation of the neuron to a high value, then the sentiment of the output text will be positive. Whereas if you set it to a low value, the sentiment of the output text will be negative. So that's like a demonstration of the principle that by identifying these neurons, that gives us some control by sort of artificially constraining their activations. So stuff like this could be very interesting for like identifying those sort of useful neurons, and maybe it will be combinations of neurons instead that you can then act on in some way. So yeah, it's definitely a really interesting avenue.
Nice. And I think that concludes the talk for now. Thank you so much, Alex. And I'll give you a hand here. There's no audience clapping. Of course, this project also came out of a wonderful hackathon and is part of the Impart Labs project too. And already this weekend, there's a distillation hackathon held by someone else. But on the 30th, there is a benchmarks hackathon, so on safety benchmarks, something that, of course, is extremely important as we move into the future. And we want to make sure we evaluate models properly. We have the wonderful Alex Pan coming to speak, who has been part of the Machiavelli paper too. And we really recommend you join, because it's going to be really rock and roll. So thank you so much for joining. And thank you so much to Alex for coming along as well. And we'll see you at the next hackathon or at the next talk. Ciao.